So my discrete time model for the rigid body motions, A is nothing but I 1 delta t 0 1. That's my discrete time model. Again, the B, because AC, the determinant of AC equal to 0, and we cannot use AC inverse, so we just use that expansions. Now I delta t plus have AC delta t square. If you check the formulations of last slide, you will be able to see that all the AC square larger than AC square, all the term involve AC square and higher power, all zeros. So my result will be delta t, this identity, and so an AC delta t, then it becomes delta t minus half delta t square and delta t, multiplied 0, 1, and 1 half delta t square delta t. That's my B. So if that's the case, my B will be delta t 0 delta t plus for AC is 0 1 half 0 1 and 0 0 times delta t square. So that becomes delta t half delta t square and 0 delta t. Of course, I have to multiply this by 0 1 and this by 0 1, then that equal to that one, delta t square, and then delta t. Right? Any questions? So convert from a continuous time to discrete time looks quite easy, right? Like that. At least for discrete time, for the rigid body motion, it's quite easy. Now, something you need to be careful here. The discrete time model is the sample time dependent. If I have a different sample time, my discrete time will be different. For continuous time, it's nothing to do with sample time. But for discrete time, if you look at this, if my delta t is 0.1, then my A is 1.11. If my delta t is 0.2, will be 1.21, 1.201. So all the discrete time is sample time dependent. Why? Why is that? Because my U. Okay? My U. My U, if I change my U, this constant in one period, if that constant one period is that period is getting smaller, then my constant for U is small, it's smaller to apply to the system, right? So discrete time model is sample time dependent. Any question about it? No. Okay. So I'm going to talk about the three motion again. These three motion will allow you to understand better. Let's talk about vibrational motions. Easy, right? I'm just assume that m equal 1, k equal 1. You don't have to assume that, but here is for simplicity. I assume m equal 1, k equal 1, and then my discrete time model. Look at my discrete time model, it's very pretty, like this. I use the same thing, the exponential functions. Now you can go home to do your exercise. Use that formulation, I plus AC delta t plus half AC squared delta t squared plus then and so on equal to, you will find out that nothing but cosine delta t sine delta t minus sine delta t cosine delta t. That's my discrete time model for A. For B, because my AC inverse exists, so I can use AC inverse to derive my B. AC inverse times 1 minus cosine delta t, AC inverse A minus I, then parenthesis BC equal to parenthesis 1 minus cosine delta t, and then sine delta t. That's my B. That's very pretty, don't you think so? With a continuous time AC, you don't see anything to do with sine or cosine. But in your discrete time model, then you get a cosine and sine, or minus cosine and sine. Any questions? Still no questions. This is important, also very important here. We know that vibrational motion has no damping. No damping. Right? So what does that mean, no damping? The AC, the eigenvalue AC, how much the eigenvalue AC for this case? No damping. So eigenvalue AC, what is eigenvalue AC? It's a plus minus I, am I right? So the eigenvalue AC eigenvalue of AC is equal to 0, 1, minus 1, 0. That's how much? Right? The plus and minus I don't have any real parts of this eigenvalue. So this is not asymptotically stable, but this is still stable because stable, right? So that's the oscillations because we have frequencies 1 million per second. Okay, now interpret to this A. So eigenvalue A. What is eigenvalue A? This eigenvalue A. Because if you look at this, this is stable, but not asymptotically stable. And the eigenvalue A. What is the eigenvalue A? See, so let us look at this. A equal to cosine delta t, sine delta t, minus sine delta t, and then cosine delta t, right? What is determinant A? is cosine square theta t plus sine square t equal 1. Agree? Now when we talk about discrete time, continuous time, you are going to understand their properties. You don't just look and say, oh, okay, because my professor showed me AC is that, my discrete time is like that, it was very pretty, that's it, you know? You don't even think about the something behind those state metrics. There's some nice properties behind this metrics. This is eigenvalue will be only pure imaginary. We know that eigenvalue will be pure imaginary because that's only vibrational motion with no damping. With no damping means it's only pure imaginary, no real parts. Right? And when you convert it to a discrete time model, that conversion has some properties we have to understand about it. First of all, your determinant is equal to 1. Equal to 1. Then we're going to discuss about the property of eigenvalues of the discrete time model. When is stable? When is asymptotically stable? That's important to design a controller, because when you design a controller, you have to make sure your system is stable or not first. Your open loop system is stable. Then when you design a closed loop controller, then you got to make sure my closed loop eigenvalue in the discrete time model is also stable, right? Then how can I know it's stable? They have some spatial nice properties of this. That's we're going to talk about that next week. I need to spend some time on that, so you understand the properties of discrete time model. Okay, now this is 3 o'clock. Do you have any questions? For those of you who don't have any questions, you are welcome to leave. The class is ended.